Okay, good morning, everyone. I want to welcome you to another theory of statistics class. Of course, we're starting chapter 6 today that we call the function of random variables. Okay, so in the outline, I'm actually going to walk you through three different methods of figuring out the function of random variable, the method of distribution functions, the method of moment generating functions, and the method of transformation. And of course, I need you to pay attention because this is highly mathematical. Okay, so when I talk about function of random variable, okay, we actually mean if I have a random variable, if x is a random variable, and if I can define y, and y is a function of s, since x is a random variable, y is also going to be a random variable. A function of random variable is also a random variable. That's what I mean. Okay? Now I'm going to walk you through the method. Okay? And we're going to go through this method one after the other because situation where they give you x, okay, maybe they give you the function of x, they give you probability distribution of x, and after giving you this, if they define y, maybe they define y, the y to be, for instance, x squared, okay, and the question asks, find the distribution of y. Please pay attention. You were given f of s to be distribution of x. Okay, if you're given f of s to be distribution of x, and we are defining a new variable that is a function of s, then the question now is, can we have a way to also figure out the distribution of y? We know the distribution of x, but we want to figure out the distribution of y, where y is a function of x. Okay, that is the focus here. Now, the first method that we can use to figure that out is what we call the method of distribution function, and I'm going to explain to you. Okay, now in the method of distribution function, we're actually going to define, we let u be a function of a random variable, y1, y2 up to yn, okay, and we define the region, okay, u equal to a realized value. We find the region where u is less or equal to u. We find the probability associated with that. The probability associated with that is what we call the CDF. Of course, in this class, we've done what we call CDF. Then, after getting this, we actually, we're going to get this by integrating over that region. And after getting the CDF, we can actually figure out the PDF. Because when I actually perform derivative on the CDF, that will give me the PDF. Now, based on what I display, please pay attention. What I display here, you are giving a probability distribution of y, because you have y1 up to yn, and you want to figure out the distribution of u. In the example here, I'm talking about x and y. But here, in what I'm projecting, I'm talking about y and u. We have the distribution for y, but we want to figure out the distribution for u. We have, based on what I'm displaying right now, you give in f of y, but u is a function of y. You now want to figure out the distribution of U. To figure out the distribution of U, we need to use what I call the method of distribution function, where we need to first find the probability of a U less or equal to a realized value. And after getting the CDF, all what we're going to do is to perform derivative of the CDF of U. Then finally, we're going to get the required probability function for U. That is how the method of distribution function work. Now, I want to walk us through an example. You know what I need you to do? I need you to focus on the board. The moment, if you get stuck or you need clarification, direct your question to me. You know what I want to do now? I want to walk you through an example where they gave you f of y, and they want you to find, and there's a new variable, and that very new variable is a function of y. They want you to figure out the probability distribution for u. Okay? And right now, we want to use the method of distribution function. Let's take a look at this example. A process for refining sugar yield up to 1 ton of pure sugar per day, but the actual amount produced y is a random variable because of machine breakdowns and other slowdowns. Of course, they're trying to tell us here that y varies. What you actually produce, the sugar produced, will vary because of the fact that, we could have situations where machine breakdowns, or at times we could have some slowdowns. Now they're trying to tell you that can be represented as, we can use a probability function to represent y, because y is a random variable, and that is given here. Take a look at that. They've given you f of y to be equal to 2y, where y lies between 0 and 1. Now, if you're given this, what is the question? Please pay attention. Now, the question continues. The only information that we got so far, it has to do with the distribution of y, where y, you've been told, y actually represent the yield, okay? The yield, okay, is the yield of sugar produced. Okay, now, I have the distribution for y. What is the next thing? The question continues. The company is paid at the rate of $300 per ton for the refined sugar, but it also has a fixed overhead cost of $100 per day. Thus, the daily profit in hundreds of dollars is given as this. Please pay attention. This is where I'm coming. I have a new variable u. It's a function of y. Of course, the u here is actually represent the profit. If I were to talk about the profit will depend on what you produce, which is y. Can you see that? Now we have this equation now. Now the question now is, if the company wants to determine the average profit or the variance of profit, the company needs probability function for u. But we do not have probability function for u right now. We only have the probability function for y. Now, this is an example of a function of random variable. Now, if y, which is the amount of sugar produced, is a random variable, then u, that is the profit, is also going to be a random variable, because when if y is a random variable, then the function of a random variable is also a random variable. Now, what we want to do here is to find the probability density function for u, because without finding probability density function for u, there is no way the company will be able to find average profits, the variance profits, and so on like that. Now, let's get started. I want us to use the method of, distribution function. It's mathematical. I need you to pay attention now. Focus on the board. Now, let's get started. Now, using the method of distribution function, I'm actually want to figure out the CDF based on u, which is going to be a capital, an uppercase F u, is going to be equal to the probability of a random variable u less or equal to a realized value. And you know what? what is my u? All what I'm going to do, I'm going to plug in my u here, which is 3y minus 1. Okay, so you can see how I go from here to here because I've been given that u equal to 3y minus 1. Now, what do I need to do? Inside the parentheses, I need you to focus attention on the parentheses now. Okay, solve for y. Solve for y. When I solve for y here, this is what I got. Is there anyone who doesn't understand how I got here? Is there anyone in this class who doesn't understand how I got here? Is there anyone? Okay, now I will have probability of y less or equal to u plus 1 over 3. You know what I'm going to do? If I want to find the probability of y now, please pay attention. Okay, I want to find the probability of y now less or equal to u plus 1 over 3. Of course, I'm actually going to make use of the f of y to do that. I've been given f of y. If you go back, you see that? The f of y equal to 2y. I'm actually going to use this. I'm going to integrate this. I'm going to perform an antiderivative on that. Okay? But, you know, less or equal to this. This is going to be the upper bound. I'm going to start from 0. Can you see that? It is starting from 0. And that actually explains. That explains what I'm doing here. Can you see this guy? Can somebody see this guy? That explains what I'm doing here. Because if I want to do that, I'm actually going to go from 0 to u plus 1 over 3 to y the y. That's what I'm going to do. Okay? And after that, it's going to give me this. U plus 1 over 3 all squared. Now, the u plus 1 over 3, or u plus 1 over 3 all squared here is just a CDF. What do I now need to get a PDF? I'm actually going to differentiate this guy. If I want to write it down in a CDF version, this is what I mean. Now, if I want to get my final answer now, I'm actually going to perform derivative of a CDF. Okay, now this guy actually, that guy actually gave me u plus 1 over 3 all squared. This guy is the CDF. This guy is the CDF. Now, I want to get the PDF. I'm actually going to do the derivative of this guy, the derivative of that. Okay, I'm going to differentiate this guy. When I differentiate that guy, this is what I'm going to have. This is my final answer now. You know what? After getting this guy, I need a state space for you. How am I going to get a state space for you? Okay, I'm actually going to show you now. Okay, I need you to go back. What do they call your u initially? Okay, u is 3y minus 1, right? Okay, u is 3y minus 1. Okay, u is 3y minus 1. Okay, what was the range of y given? Initially, is 0 to 1. Okay, I need the range of y to figure out the range of u. Okay, when y equal to 0, what is my u? U is going to be 3 into 0 minus 1. That is going to be negative 1. When y equal to 1, okay, I actually want to figure out that. That is going to be 2. That means what I figure out now is that u lie between negative 1 and 2. Now, I'm actually going to show you what I have now. That was why we have this guy here. U lie between negative 1 and 2. And you know what? If you want to verify whether your answer is right, if you want to verify this answer here, all what you just need to do is to perform antiderivative on this guy from negative 1 to 2. If you perform an antiderivative on this guy from negative 1 to 2, can somebody tell me what the answer is going to be before you can actually boastfully say you are right? What would the answer be? Go ahead. 1. Thank you for sharing that. It has to be 1. So if you want to verify your answer, you're actually going to perform, you're going to do the integral. of this guy from -1 to 2. That should give you 1. Now, if that is right, then you can now proceed to actually, maybe there's any other thing you want to find, like expected value of u, a variance of u. Like if I have the f of u, now I can get the expectation of u. To get the expectation of u, it's just going to be integral u f of u du. I can also get the variance of u. Now that is how we use the method of distribution function. But right here, this is method of distribution function for one variable. I move from, why do I say one variable? 1 to 1. I move from variable y to variable u. But what if in a situation? At times, we may want to move from 2 variables. How are we going to achieve that? I need you to pay attention. It's getting complicated. But you know what? I need you to focus on the ball. Now, let's take a look at this example. Now, if we have a random variable y1, which is the amount of gasoline stocked at the beginning of a week, and y2, the proportional amount of gasoline sold during the week. y1, you see what y1 represents? What you stock, okay, at the beginning of a week. And y2, what you sold out, okay? Now, the joint density function of y1, y2 is given as this. This is a joint. I have 2 variables now, y1, y2. This is the joint. But the new variable now that we are interested in, find the probability density function of u, where u is y1 minus y2. y1 minus y2, that is the proportional amount of gasoline remaining at the end of the week. Of course, when I subtract what I have in the beginning, okay, when I subtract what was sold from what I stock in the beginning of the week, then I'm actually talking about the outstanding. The outstanding is u. That very u is a random variable. Why is u a random variable? Because y1 is a random variable, y2 is a random variable. But you know what? That's a lot of question here. Find the probability density function of u, and after that, they wanted to find the average, the expectation of u. It is only when you get the function of u correctly that you will be able to obtain the expected value of u. But you know what? I need you to pay attention. 2 variables are involved. Now, I have y1, y2. I want to go to u. How am I going to do it? Pay attention. Now, please pay attention like I said. I want to use a method of CDF, f of u, which is equal to probability of u less or equal to u. That's a CDF. That's the method we've been using. Okay? And you know what? If I want to go by complementary law, okay, the probability of u less or equal to u plus the probability of u greater than is going to be equal to 1. So I can say this equal to 1 minus that. Please pay attention. If it is equal, now we know what I want to do. I want to figure out the greater than 1. If I want to figure out the greater than 1, don't forget, because I got 2 variables involved, okay? Now, I need to determine what would be the, this guy here is actually the 3y1. Where is the 3y1 coming from? That is the joint given. That is the joint, okay? You can see the joint given. I'm actually writing the 3y1 here, and I'm going to write the y2, the y1. Now, the y2 here, the range of the y2 is from 0 to y1 minus u. How do I get that? Let's take a look at what we have now. Okay, so this is y2. Or if you look at here, solve for y2 here. The y2 here is going to be what? If you solve for y2, that should be y1 minus u. You know what I'm talking about? Pay attention. You don't understand. Ask questions. Like I said, Okay, I'm looking at the relationship now to figure out. So right now, okay, I got u equal to y1 minus y2. Okay, what is y2 from here? Okay, so what is y2? Y2 is y1 minus u, right? That's y2, right? Now, the range of y2 is actually, the range of y2, 1 second. Okay, let me see. Okay, 1 second. Okay, I'm gonna, okay, should be working now. Okay, so, okay, now, let me go to what I was explaining. Now, right now, you see, 0 to y1 minus u. So the same thing here, if I want to find y1. If I want to find y1 is, the y1 is going to be that plus that. So y2 is equal to that. So now, when you take a look at what I have, okay, the first one is going to be u to 1. And the second one, why do I say u to 1? Is because this is, you can say this is greater than, right? Greater than u, we mean u is going to start from that u. What is the upper bound? According to the range of y is 1. So that was why you see u to 1. Okay? Then after u to 1, then the other one is going to be 0 to that. So what I'm going to do, I'm going to do sequential integration. And at the end of the day, I got this when I do sequential integration. Now, this guy here is the CDA, but that is not the final answer. Then to get the final answer, I need to differentiate this guy. Now, differentiating that guy, differentiating this guy will give me this. Now, the final answer now is this guy. This is the f of u. Now that I got this as f of u, I can get the mean. Okay, I can get the mean of that. Let me come here. Like, if I want to get the mean now, all what I'm going to do, since my f of u equal 3 into 1 minus u squared over 2, and the range is that. So my f of u is going to be integral u f of u du from 0 to 1. So what I'm just going to do, 0 to 1, u, 3 into 1 minus u squared over 2 du. I will just focus on that. Now I'll get my f of u. I'll get my expected value of u. I can also get expectation of u squared. Okay, I can get expectation of u squared, okay, using u squared f of u du from 0 to 1. From there, I can get the variance of u, which is expected value of u squared minus expected value of u all squared. Okay, so the moment we are able to establish f of u, the other one is going to be super easy. Okay, now if that is actually taken, the next that I want to talk about is, I'm going to go into another example now. Now, I'm going into another example now. Okay, what if in a situation where you are given a variable, you have a function of y, which is h of y, and you now define a new variable. The new variable is y squared. Let me tell you this. the distribution of y is different from distribution of y squared. I'm going to say that again. The way variable y is being distributed is different from the way variable y squared is being distributed. So if you take a look at what we want to figure out now, if we know the distribution of y, but we want to figure out the distribution of y squared, that distribution of y can be any form of distribution, okay? And I need you to pay attention, okay? I have f of y. That f of y is a distribution of y, but I want to define a new distribution. I want to define distribution for u, where u is equal to y squared. I want to use the method of distribution function, which is the probability of u less or equal to u. You know what I'm going to plug in? What is my u, y squared? I'm plugging that here. Can you see that? Then when I plug that here, I want to find the probability of y squared less or equal to u. If I have a probability of y squared less or equal to u, if I have the probability of y squared less or equal to u, if I have the probability of y squared less or equal to u, don't forget, this is the CDF that I want to find, okay? That is the CDF, right? Now, the probability of y squared less or equal to u, the fact that then I need to solve for y. To solve for y, this is going to have a square root, but it's going to have, there's going to be plus or minus. You remember? That's a quadratic. There's going to be plus or minus, and if there's a plus or minus, I can rewrite that as this. I can write y lying between the negative of square root of u and the positive of square root of u. So what I'm trying to say, this guy is the same thing as this guy. Y squared less or equal to u is the same thing as y lie between negative root of u and that. Now this is what now you know what I'm going to do here. I now want to find the probability of y, okay, using, I'm going to use the f of y, whatever f of y given. So here now, I'm going to do the probability distribution, the limit of the integration is going to be negative square root of u to u, f of y dy. If I perform an antiderivative on f of y, I'm actually going to have a CDF. So this is what I'm actually saying. Okay, integral of f of y, the y, is going to give me this. Antiderivative of a PDF. PDF is a lower f. CDF is an upper f. Now, imagine I said I want to do this. Square root of that plus square root of that. Okay, which means when I integrate this one, I got this, then I'm going to say from negative square root of u to that. Okay, then I'm going to plug in this guy here minus when I plug in this guy. So which is going to be f square root of u minus f negative square root of u, which is why you have this guy here. Okay? Now, if you have that guy now, please pay attention. It's becoming more mathematical. This is at this stage, I expect the class to be full to the brim. I expect a lot of students in the class right now. You know why? Because the chapter that we are starting now is actually going to dominate the final exam. And that's why you have to be around. I've been posting my recordings now. So I posted 3 videos, was it maybe 2 days ago. You can check my YouTube channel, okay, because we're moving very close to the final now. Now, if I have this as a CDF, what I have here now is the CDF, and I want to get a PDF. I'm going to differentiate this guy. Please pay attention. How do we differentiate it? So differentiating this, please pay attention. If I want to differentiate this guy, square root of u actually means Square root of u means u raised to power half, mathematically. You know what you're going to do? Let's differentiate this. I want to differentiate the whole of this. Okay? Differentiating this, I will first write a lowercase. I will block this. I will differentiate what is inside as well. Now, differentiating what is inside, d du of that is going to be, I'm going to have half here. This is going to be -1. And this is going to be half, because this is u raised to power minus half. And u raised to power minus half, when it goes down, u raised to power half, this is the same thing as that. Which is what I'm doing here. Take a look at that. Can you see that? 1 over that, then that plus that. I'm done. This is the PDF. This is the PDF. Okay. I'm done with the method of distribution function. And I want to go to another method that we call moment generating function. The method of moment generating function is easy because, of course, in this class, we've done moment generating function before. Now, take a look at this. Let y1, y2 up to yn be independent random variable. What do we want to do here? Oh, if y1, y2 up to yn are independent random variable, and I have a moment generating function for y, but I'm seeking to get a distribution for new variable. And what is the new variable u? The new variable u is when I had y1, y2 up to yn. Do you know that if I know the moment generating function of a probability distribution, I can figure out the distribution? If I'm in Texas, let's say I'm in Texas, and somebody said is from Minneapolis, where do you think which state in the U.S. do you think my mind is going to go to? Minnesota, because it said Minneapolis. So if I know the moment generating function of a particular, maybe a random variable, I can easily say the distribution that particular random variable belongs. But you know what? In this class, we have learned about a lot of moment generating function. If I know the moment generating function of y1, y2, up to yn, if I actually seeking to get the moment generating function of a u, which is a sum of the random variable, then the law says I should use the product of the moment generating function of the respective variable. This is the law. If u equal to y1 plus y2 up to yn, if I want to get the moment generating function of the sum, all what I just need to do is to multiply the moment generating function of the respective random variable, okay, which is what I'm doing here, if you take a look at that. Therefore, that is exactly what I'm trying to say. Now, how are we going to use this? Okay, the moment I'm able to get the moment generating function of the sum, then I can get the mean, I can get the variance. Okay, now, and in this class, I remember I walk you through this. If I have y1 up to yn, and each of them follow normal distribution, in such a way that the mean of y1 is mu1, the variance of y1 is sigma 1 squared, the mean of y2 is mu2, the variance of y2 is sigma 2 squared. This is the general way of writing that. Instead of yi equal to mu I start from 1 to n. The variance of yi equal to sigma I squared. Because they are independent, covariance will be 0. I'm only going to have the variances. Did you know that if I want to find, if I want to rewrite u now, if u is a linear combination, where we have a 1y1 up to that, then the mean is just going to be this guy here. The variance is just going to be this guy here. Okay, that's what I mean. Now, I need you to pay attention. It's getting critical. Okay, now, if I have this guy, I want to focus on this guy. Okay, now when you take a look at that guy, Let me see if I can. Can I write something? Okay. Do you see that guy? That guy is a moment generating function of a random variable that follows normal distribution. Why do I put I? I'm going to substitute I for 1 if I'm focusing on Y1. If I'm focusing on Y2, moment generating function for Y2, where Y2 follow normal distribution, wherever I see I plug into. Okay, now, you know what I want to do? I want to find, if you take a look at what I have right now, okay, if this is a moment generating function of Y, what is the moment generating function for AIYI? I know moment generating function for Y. Can I figure out the moment generating function of a linear combination? AIYI, that's what you see. The moment generating function of the linear combination is just going to be that. Look at the difference between the two. The other one, just mu I t plus sigma I squared t squared over 2. That is just for a particular Y. But what about the one for the linear combination? Like AIYI. Maybe I want to get what is the moment generating function for this. For this guy here. UI, which is AIY1. What is the moment generating function for U2? A2Y2. That's what I mean. So what is the moment generating function of UI, AIYI? I start from 1, 2 until we get to N. Now, this guy now is the moment generating function for AIYI. If I wanted to know for Y1, okay, for A1, if I want to know for U1, which is A1, Y1, wherever I see I, I'm just going to plug in 1. But you know what? If you come back here, please pay attention. If you come back here, look at this guy. That is U1, U2, up to UN. So I want to get the moment generating function for general U. General U equal A1U1 plus A2, and so on like that. Now, when you take a look at the general U, this is U1, okay, the U2, and so on like that. Okay, now, but you know what? I know the moment generating function, okay, for this guy. I know the moment generating function for this guy. I know the moment generating function for this guy. If I want to seek the moment generating function for this guy, I will multiply the moment generating function of each component, which is what I'm doing here. Okay? Moment generating function for A1, Y1 multiplied by moment generating function for A2, Y2 until I get to that. A1, Y1 is U1. A1, Y1 is U1. But we want to get the moment generating function. We want to get the moment generating function for general U, which is U1 plus U2 until we get to UN. Okay, that's what we want to get. Where this guy is A1, Y1, A2, Y2 until we get to AN, And what I'm trying to say is that the moment generating function for the general U, is actually going to be the moment generating function of this guy here, okay, of this particular guy here, multiplied by this up to that, which is what you're seeing here. Now, if I now want to write it out, okay, this guy, this is the moment generating function, this guy, you know, until I get to this. Take a look at that. And I can write that in general form because this is going from mu1 A1, mu2 A2 until I get to UN AN. I can rewrite this as the general formula, you know, in a short form. I can write that in a short form. When I write that in a short form, okay, so when I write that in a short form, then what I'm going to actually have now I can boastfully say, oh, this is also a normal distribution with the mean of this. This is the mean. Because the convention, the simpler one, if you take a look at, if y follow normal distribution, the moment generating function is this guy, mu t plus sigma squared t squared over 2. So this is the mean. This is the mean. Now, here, this is going to be the mean, because this is a t. The whole of this is going to be the mean. And this guy is the mean of the linear combination that I showed you the other time. I'm going to show you now the mean of that. Can you see that? This guy here? Summation A high, U high is the mean of that linear combination. So which is exactly what you can see here. Okay? And this is going to be the variance. That will be the variance. So with the moment generating function, I can talk about the mean and the variance. Like the mean is mu, the variance is sigma squared here. But don't forget, I'm assuming each of them follow normal distribution. Each of them follow normal distribution. Okay? So, is there any question? Is there any question? Okay, before I go today, if there's anyone who is struggling in my class, I remember yesterday I was in my office hour and nobody visits. So if there's anyone who is struggling in my class, make sure you reach out. The makeup opportunity, I want to believe by now you've read the announcement that I made. Announcement that I made about makeup opportunity. Okay, so the makeup is going to be posted on Friday, like I said, and it's going to be left open for until 11:59 p.m. on Sunday. So you actually going to, this program, you're going to use 15 minutes. 15 minutes, you know, but for those with accommodation later, of course, they're going to use extended time. Make sure you do not use more than the required minute. Like I said, it's not compulsory. Okay, it's not compulsory. I'm going to say this again. It is very fine if somebody struggles in a class. But what I will appreciate is I wanted to reach out. Because of the Canvas issue, you know, last time, I was not able to, because in a way, some students sent me messages, I was not able to get that. When I got that, I saw that in my spam folder. I just replied to them. So if you send me a message and you have not received a reply from me, probably didn't get to me, and I need you to send me back, you know, I need to resend the message. Now, lastly, before I go, there's a good news. So there's a good news. The good news is I've just been nominated for Excellent Teaching Award, so by my department. So I'm seeing that as good news for me. But you know what? Even though that's a good news, but the better good news, the excellent good news, is when the students in this class, the minimum score in this class at the end of the semester is 99%, which is possible. Okay? You make sure you work towards that. You can achieve that. That's all what I got for you today. Make sure you all stay safe and have a lovely day. Bye for now, everyone.